Micromeritics is the science and technology of studying particles within the range of micrometer. Micrometer is equals 10 to the power minus 6 of a meter. Okay, as we mentioned, micromeritics is the science of studying small particles within the micrometer range. The importance of studying particles within the micrometer range, it affects the release and dissolution, it affects the absorption and drug action, it affects physical stability, and it affects dose uniformity. As we discussed previously in mass transfer, that reduction of the particle size and the increase in the surface area, they influence the release of a drug from a dosage form. The higher when we have high surface area, then we allow intimate contact of the drug with the dissolution fluids in vivo, and this will increase the dissolution and drug solubility. It is also worth mentioning that reduction of the particle size increases the solubility when the particle size is extremely low, when we are working within the nanometer range. But in the micrometer range, the drug solubility is not really affected significantly by reducing the particle size. Absorption and drug action. Particle size and surface area influence the drug absorption and therefore the therapeutic action. When we increase the dissolution, then we increase the rate of absorption, we will have a greater and faster drug action. The physical stability, usually the particle size also affects the physical stability based on Stokes law. So when we reduce the particle size, we reduce the rate of sedimentation in case of suspensions and emulsions. And this will improve the physical stability of the formulation. Dose uniformity, a good flow property is extremely important in the manufacturing process of solid dosage forms such as tablets and capsules. If the flow if we have a problem with the flow, then the flow will affect the dose uniformity, and therefore the product will not pass the content uniformity, which will be discussed later. Micromeritics includes particle size and size distribution, particle shape and surface area, the pore size, the also derived properties of powders such as porosity, packing arrangement, density of particles, bulkiness, flow properties, and compaction. These topics will be discussed later. When we have a collection of particles of more than one size, which we call polydisperse, there are two important properties that we need to determine: shape of the particle and surface area of the individual particle. Second, the size range and the number or weight of particles present, and hence the total surface area. The size of a sphere is usually expressed in terms of its diameter. When we have particles that are asymmetric, then it is difficult to express the size in terms of a meaningful diameter. Therefore, under these conditions, we use the equivalent spherical diameter. The equivalent spherical diameter relates the size of the particle to diameter of a sphere having same surface area or volume or diameter, depending on the method that is being used. When we say ds, it is a surface diameter, and it is the diameter of a sphere having the same surface area as the particle. When we say volume diameter, dv, it is the diameter of a sphere having the same volume as the particle. When we use, say, dp, our projected diameter, it is the diameter of a sphere having the same observed area as a particle when viewed normal to a stable plane. When we use dst, or Stokes diameter, it describes an equivalent sphere undergoing sedimentation at the same rate as the asymmetric particle. Projected diameter is obtained by microscopic techniques, while the Stokes diameter is determined from sedimentation studies on suspended particles. When we have a large number of particles, or what we call particle size distribution, then particles will have different diameters, and we need to determine an average particle size or diameter that can describe the batch or the powder. Edmondson described a general equation. Okay, this is Edmondson's equation that can be used to determine the average particle size. N is the number of particles in a size range. P is an index related to the size and the type of mean that is being used. Summation of nd to the power f is the frequency in which a particle in a certain range occurs. P could be 1, 2, or 3 for length, surface, or volume. F also can be 0, 1, 2, or 3 for number, length, surface, or volume. The application of the equation will be shown in the next slide. The following table shows how the Edmondson's equation can be used to describe different diameters. For example, if we decide to use the size parameter P as length, and if we decide to use the frequency as number, then according to the equation we have summation of nd divided by summation of n, and it is called length, number, mean, diameter. Another example, if we decide to use, for example, parameter P as length and frequency as surface, then we have the following equation, which is summation of nd cubed divided by summation of nd squared, and it is called volume surface or surface weighted mean diameter. It is important pharmaceutically because of the it is inversely related to the specific surface area. Frequency distribution curve is obtained when we plot number or weight of particles within a certain range against size range of mean particle size. This is shown in slide number 10. Frequency distribution curve gives a visual representation which is usually not achieved by determining only the average diameter. For example, two batches might have the same average diameter, but the behavior is totally different because the particle size distribution is different. The size that occurs at the highest frequency is called the mode. Mode, median, and mean will be the same if we have normal distribution only. Another method of representing the data is to plot cumulative percentage plot over or under a particular size versus particle size. This is shown in slide number 13. The standard deviation can be determined using this equation, which gives an indication about distribution around the mean. Frequency for normal distribution, 68% of the population lie within plus or minus 1 standard deviation of the mean. 95% lie within the mean plus or minus 2 standard deviations, and 99.7% of the population lie within plus or minus 3 standard deviations. The following table shows how to calculate diameters from data obtained using microscopic method. For example, different particles might have different particle sizes. If we have 118 particles, 2 of them might be in the size range of 0.5 to 1 micrometer. If we have 17 of them, also might be in the size range of 2.5 to 3 micrometer, for example. And we can use these values, the average size range multiplied by the number of particles, to determine the ND, or diameter square multiplied by the number of particles to determine ND square, etc. Then we can use either summation of ND, summation of ND square, or summation of ND cube to calculate the average diameter based on Edmondson's equations. This figure shows a frequency size distribution curve. As I mentioned before, the size that occurs at the highest frequency is called the mode. According to this figure, the mode equals 2.2 microns, and more than 50% of the population have a mean size range of 2.2 microns. This table shows how to convert number distribution into weight distribution and how to calculate the cumulative percent frequency under as a number and as a weight. Percent of n is calculated by dividing the number of particles, for example, by the total number of particles and multiply it by 100 to get, for example, the 1% in this case. Cumulative percent frequency under size is obtained by summation of percent n. For example, 1 plus 16 equals the 17%. So in this case, the number of percent frequency under size and this range of size is 17%. In order also to determine the cumulative percent frequency under size as weight, we need to determine the ND cube, and then we determine the percent ND cube, and in a similar manner we can obtain the cumulative. For example, the cumulative percent frequency under size of 5 micron equals 2.34, which is the summation of 0.03 plus 2.31. This figure shows that the percent frequency size distribution calculated as number and as weight are totally different. For example, the mode in case of number distribution is approximately 6 microns, while the diameter obtained from weight distribution is approximately 10 microns. The cumulative frequency plot also shows a difference between number and weight distribution. For example, 50% of the particles have a particle size less than 8 microns as number of distribution, while the same 50% of the particles have less than 12 microns as weight distribution. The difference between number and volume distribution is shown in this figure. Let's assume that we have 9 particles. 9 particles, 3 of them having a diameter of 1 micron, 3 of them having a diameter of 2 microns, and 3 of them having a diameter of 3 microns. If we calculate the number of distribution, then 1/3 of the particles will have a diameter of 1 micron, 1/3 will have diameter of 2 microns, and 1/3 of them will have a diameter equals 3 microns. However, if we calculate the volume distribution, you will find that the volume of small particles is extremely small compared to the volume of large particles. Therefore, the percent by volume of the large particles is huge compared to the percent by volume of small particles. Since the volume is related to the diameter cube, it will be different than the area which is related to the diameter square, and will be different than looking at the particles as number only. This table shows the particle dimensions in pharmaceutical dispersed systems. For example, suspensions and fine emulsions have particle size range 0.5 to 10 micrometers. Coarse emulsions and flocculated suspension particles have particle size range from 10 to 50 micrometers. Fine powders have particle size range of 50 to 100 micrometers. Coarse powders have particle size range of 150 to 1000 micrometers. Granules are usually large and they have diameter between 1 to 3.36 millimeters. The particle size is usually determined using one of the following methods: optical microscopy or sieving, and it will be discussed later, sedimentation, Coulter counter, electron microscope, and other methods. basic guide to the range of particle size applicable to each method. For example, if we have particles larger than 1 micron, 1 millimeter, then the sieving method should be applied in order to determine the particle size. The size of particles smaller than 0.01 micrometers should be studied using either electron microscopy or ultracentrifuge method. Particles between, for example, 10 to 100 microns can be studied using optical microscopy, sedimentation, Coulter counter, or air permeability method. This figure shows the sieving methods. The sieves are usually arranged in a nest of 5 with the coarsest at the top. The coarsest is usually at the top. Powder is placed on the top sieves. Then the sieves are shaken for a period of time. The powder returned on each sieve is then weighed. Standard sized sieves are usually available to cover a wide range. As I mentioned earlier, the sieves are arranged with the coarsest at the top. Then the powder is placed on the top sieve and the sieves are mechanically shaken for a predetermined period of time. The sieving errors in the method can arise from number of variables including sieve loading. The sieve loading should be constant because changing the loading will affect the results obtained. Duration and intensity of agitation can also affect the sieving method. Care must be taken to ensure reproducible techniques are employed so that different size distributions between batches are not simply due to different sieving techniques. For example, change in the agitation method might change in particle size, and this might affect the results obtained using the sieving method. Usually, as I mentioned before, it is used for particles within the range of 40 to 9,500 micrometer. This table shows the relationship between the assigned number and the size of the sieve opening. The assigned number 2 is related to the number of openings in a certain area. The number means that when we have 2 large openings, the size of each opening is 9.5 millimeters. Number 35 means that 35, for example, means that we have 35 openings within the same area and the size of each opening is 500 micrometer. When we increase the assigned number, the size of the opening is reduced. Usually students ask me, do we need to memorize this table? And the answer is no. Regarding the microscopy as a method for determination of the particle size, we have the optical microscopy and the scanning electron microscopy. The optical microscopy covers the range from 0.2 to 100 micrometer, while the scanning electron microscopy from 0.001 to 10 micrometers. Emulsion or suspension is usually mounted on a slide and placed on a mechanical stage. Then the eyepiece is fitted with a micrometer by which the size of the particles can be estimated. The fields can be projected on a screen. For example, can be projected on a screen where the particles are measured more easily. Microscopy as a method has advantages and limitations. It detects the presence of agglomerates. Therefore, this method should be used even with other methods in order to detect agglomerations and aggregation of particles. The limitation of microscopy is that it covers only 2 dimensions instead of 3, because we cannot estimate the thickness of the particles. Also, it is time consuming. It's a slow method. We need to count 300 to 500 particles in order to get a good estimate for the particle size distribution. Okay, when we discuss the measurements using under the microscope, we have different methods to calculate the diameter. We have the Martin diameter, which is the length of a line that bisects the particle image. This is the Martin's diameter. Ferret's diameter, distance between 2 tangents on opposite sides of a particle parallel to some fixed direction. Let's assume this is the shape of the particle. This is the shape of the particle, and these are the 2 tangents that are opposite to each other. Projected area diameter is the diameter of a circle with the same area as that of a particle. For example, this is the projected area, which is almost the same as the area of the particle. So let's assume that this is a particle. Then this is the ferret's diameter. This is the Martin's diameter of the particle. Okay. Regarding the Coulter counter method, it is used to cover or to measure the particle size within the range of 0.5 to up to 300 micrometer. It is a particle volume measurement. In this method, the powder is suspended in an electrolyte solution. The suspension flows between, or the suspended particles flows between 2 electrodes, and resistance is measured. There is a peak in resistance when particles pass, and the amplitude is related to the particle size. This figure explains how the Coulter counter is working. As you can see, when the particle passes, there is a resistance, and the instrument measures the resistance, and the resistance is related to the particle size. Particles suspended in a conductive electrolyte solution. As you can see, the particles passes. Okay. A DC current is applied, creating sensing zone. As each particle passes through the opening, it displaces an amount of saline, which is sodium chloride, equivalent to its size, creating resistance or impedance, resulting in voltage pulse, which is proportional to the particle volume. Okay. Regarding sedimentation method, it covers a range between 0.8 and 300 micrometer. The diameter obtained equal or equivalent to a sphere falling at the same velocity as that of the particle under consideration. The particles should not aggregate, because if particles aggregate, then they will settle rapidly according to Stokes' law. And therefore, sometimes if a deflocculating agent is used to assure that the particles are separated and they do not form aggregates or agglomerates. The Anderson apparatus is usually used to measure the particle size using the sedimentation method. It consists of a vessel or a cylinder of 550 ml. It contains a pipette. The lower tip of the pipette is 20 centimeters below the surface of the suspension. Then we prepare 1 to 2% suspension of particles, and it is introduced to the cylinder or the vessel. At various times, samples are withdrawn. This figure shows the Anderson apparatus. As I mentioned earlier, it is a cylinder or a vessel, okay, that contains a pipette, okay. And the suspension is usually added to the cylinder, and samples are withdrawn within a certain or specific time intervals. The obtained samples are usually analyzed, and the particle size is determined using Stokes' law. According to Stokes' law, it relates the rate of sedimentation, which is height divided by certain time, but the rate of sedimentation is related to the diameter. It is also related to the difference in the density between the particle and the dispersion medium, and it's also related to the viscosity of the dispersion medium, and this is the diameter or Stokes diameter that is obtained from the Stokes law. In certain situations, ultracentrifugation is used instead of gravity acceleration to determine the particle size of polymers. Regarding particle shape and surface area, particle shape, the shape of the particle usually affects the powder flow. It also affects the packing properties and the surface area. Surface area is per unit weight or volume. It is extremely important when we are talking about adsorption and dissolution studies, since the adsorption and dissolution are both affected by the surface area. Sphere is usually has the lowest surface area per unit volume, and when we have asymmetric particle, we expect that the surface area will be higher than the sphere. The surface area, or the specific surface area, is the surface area per unit volume or unit weight. How the surface area is usually determined? Either using the adsorption method, which is the most popular method, or by using air permeability method. In case of adsorption method, the amount of gas, mainly nitrogen, adsorbed on the surface is a function of surface area of the particle. So if we can determine the number of moles of nitrogen necessary to cover the surface, and if we know multiplied by the Avogadro's number, then we know the number of molecules required to cover the surface, multiplied by the cross-sectional area of the nitrogen molecules, which is 16.2 angstrom square, then the surface area of the powder can be determined. Regarding the air permeability method, it depends on the resistance to the flow of the fluid, such as air, through a plug of compacted powder. When we have small particle size, then we have resistance to the flow, and it will be greater, and from this part the surface area can be determined. The surface area of powder is usually determined using the adsorption method. The linearized form of the BET equation is usually used to determine the Vm, which is the volume of gas required for monolayer coverage. This equation was discussed in Pharmaceutics 2 Interfacial Phenomena chapter. V is the volume of gas adsorbed. P is the pressure of the gas. P naught is the saturated vapor pressure of nitrogen. B is a constant relate that expresses the difference between heat of adsorption of the gas in the first layer and heat of condensation in successive layers. Once Vm is being determined from the slope and the intercept of the linearized form of the equation, then the specific surface area can be calculated. Using this is the equation that is used to determine the specific surface area. Molecular weight divided by the density is the molar volume. So if we divide the volume required for monolayer coverage by the molar volume, the number of moles required for monolayer coverage is determined. If the number of moles is multiplied by Avogadro's number, then the number of molecules is being determined. If this is also multiplied by the cross-sectional area of the gas molecules, which is in this case 16.2 angstroms square in case of nitrogen, then the surface area is determined. This is a typical plot of an adsorption isotherm, amount adsorbed versus relative pressure. This is a type 2 isotherm, where the heat of adsorption is higher than the heat of condensation. The data that are usually used in order to determine the specific surface area using the BET method are usually between 0.1 relative pressure up to 0.3 relative pressure. So this is the range that is usually used in order to determine the specific surface area. This is a linearized form of the BET method, our BET equation, which is coming from Brunner, Emmett, and Teller. As you can see, we can obtain the slope of this figure and also the intercept. Using the slope and the intercept, we can determine the volume required for monolayer coverage, and this is the Vm which is used in order to determine the specific surface. Properties of powders, mainly porosity. Suppose that we have a non-porous powder placed in a cylinder. When the powder is placed in the cylinder, the total volume occupied is known as the bulk volume. In this case, the bulk volume equals the true volume of the powder plus the volume of spaces between the particles. The void volume or the volume of spaces is the difference between the bulk volume and the true volume of the particles. In order to determine the porosity, we determine the void or the space, the void volume, and we divide it by the bulk volume in order to determine the porosity. And it is usually expressed as percent porosity. Densities of particles. Why do we need to discuss density in the chapter of micromeritics? Well, particle size usually affects bulk density, and this will affect the flowability of powder, and flowability will affect content uniformity. We have different types of density. We have the true density, which is the weight per volume. But which volume? It is the volume exclusive of the voids and interparticle pores. If the powder is non-porous, then the true density can be determined using either helium or liquid displacement method. For porous powder, we need to use helium displacement method because helium molecule is extremely small and can access pores. Granule density is usually determined using mercury displacement since the mercury is large and will not be able to access pores smaller than 10 micrometer. In the lab, water was used instead of mercury for safety reasons since mercury is toxic. Bulk density is usually determined from the bulk volume and the weight of dry powder in a graduated cylinder. Tapped density is usually determined by measuring the volume in a certain weight after tapping for 1,000 times. Flowability or flow properties. The flow of particles is usually affected by the attractive forces between molecules. Flowability is extremely important in manufacturing process, mainly tablets and capsules. Powder flow will affect the production of uniform dosage form. Factors affecting flowability. These include particle size, particle shape, porosity and density, surface texture, which is being rough or smooth, for example, and moisture content. Small particles usually have problem with flowability. Particles smaller than 10 micrometers mainly have this problem. In this case, cohesive forces equals gravitational forces. When the particle size is increased, gravitational forces facilitate the flow. This is true as long as the size of the particle is smaller than the opening. Flowability can be improved by removing fine particles that are extremely small, or by absorbing these particles into larger particles. Particle shape also affects the porosity, and this will affect the flowability. Particles that have high bulk density usually do not have problems with flowability. Moisture content. Moisture content usually increases up to a certain level, of course, increases the attractive forces between molecules. Therefore, drying might reduce cohesive forces between the particles, and this will improve flowability. There are several methods that can be used to evaluate flowability. Compressibility index, Hausner ratio, angle of repose, rate of tamping, flow rate, and free flow through an orifice. The first three methods are the most popular and will be discussed in this section. Compressibility index equals the difference between the tap density minus difference between tap density and bulk density divided by the tapped density and multiplied by 100. When the powder has high bulk density, then the difference between the tapped and the bulk density will be extremely small and the flow will be excellent. Hausner ratio. Hausner ratio can be also used to characterize flowability. The Hausner ratio equals the tapped density divided by the bulk density. The bulk density is usually lower than the tap density. When the difference between tap density and bulk density is small, then the Hosner ratio will be close to 1 and the flow will be excellent. When the bulk density is low, Hosner ratio will be higher than 1.5. The powder flow will be poor. In this case, addition of glidants to improve the flowability, such as magnesium stearate, starch, or talc, will not improve the flowability. If the Hosner ratio is between 1.25 and 1.5, addition of glidants will be able to improve the flow. The angle of repose. The figure that describes the angle of repose is shown in slide number 43. The frictional forces can be measured using the angle of repose. Angle of repose is the maximum angle possible between a surface of a pile of powder and a horizontal plane. The tangent of the angle of repose equals the coefficient of friction between particles. For rough and irregular surfaces, the angle of repose is usually high. The angle of repose, this figure shows how the material is being added to the pile until the friction of particles is in equilibrium with the gravitational forces. This is the angle of repose. The flowability will be excellent if the angle of repose is less than 20, and the flowability will be poor if the angle of repose is greater than 40. Compaction. Tablet compression and compaction. Compaction of powder is a general term used to describe the situation in which the materials are subject to some level of mechanical force. The physics of compaction may simply be stated as compression and consolidation of a two-phase system due to the applied force. Compression force affects surface area, granule density, porosity, tablet hardness, and disintegration. Previous investigators found that when powders were compacted under a pressure of 5 kilograms per centimeter square, the porosities of the powder composed of rigid particles such as sodium carbonate were higher than the porosities of powder in closest packing as determined by tapping experiment. These powders were dilated, that is, that they showed unexpected expansion rather than contraction under the influence of stress. In the case of soft and spongy particles, such as kaolin, the particles deformed on compression and the porosities were lower than after tapping the powder down to its condition of closest packing. Compaction also affects the specific surface area. For example, the specific surface area of sulfathiazole increased to a maximum, then decreased. The increase in surface area was due to creation of new surfaces when the material is fragmented. Later, the decrease in the specific surface area was due to cold bonding between particles. The porosity also decreased and the density increased as a function of compression force up to a certain force level. The tablet hardness and fraction resistance also increased by increasing the compression force.